Chapter 8, Section 5, Polar Equations and Graphs. So you and I are very familiar with the rectangular coordinate system, also called the Cartesian plane. In it, we graph equations with every point in the plane being specified by two numbers, x comma y. An ordered pair is what we call it. We have an x-axis and a y-axis, basically two perpendicular axes. But now here in chapter 8, section 5, we want to graph polar equations. So what we're going to do is we're going to focus on a polar coordinate system, which is all based on a point called the pole and a ray called the polar axis. Here's a picture to go with the definition for the polar coordinate system. Here in this picture, you can see that the pole has been placed at the origin of our rectangular coordinate system so that the polar axis actually coincides with the positive x-axis. Point P here has rectangular coordinates x comma y, of course, but point P can also be located by giving the directed angle, theta, from the positive x-axis, right? There's theta from the positive x-axis. To ray OP. This is the ray OP, if I can label the origin O there. So there's the ray OP. And the directed distance R, right? R is the distance from the origin to that terminal point P there. What's really important is to note that if R is positive, then point P lies on the terminal side of angle theta. But if R is negative, that means the opposite direction, which would be over here. If R is negative, then point P lies on the ray pointing in the opposite direction of this terminal side of theta. Okay? This diagram here shows the rectangular axes superimposed on a polar coordinate grid. What I really want you to notice here is that, see, this would be our ray going from the origin to this point here. This is for when R is positive. If R is negative, notice that theta is the same, but R just being negative just means the opposite direction on the terminal side, right? So the opposite direction there. Now, as far as the relationship between rectangular and polar coordinates, if a point has rectangular coordinates x comma y and polar coordinates r comma theta, then these coordinates are related as follows. Now, what we do know is that x is the same thing as r times cosine of theta. Now, we've said that in an earlier lesson. And we also know that y is equal to the product of r and sine of theta, right? We know that r squared is equal to x squared plus y squared. In a previous lesson, we said r is equal to the square root of x squared plus y squared. And then theta must satisfy that tangent of theta is y over x. Of course, x here not being equal to 0, or else that would be undefined. Check out this first example. Plot each point in the polar coordinate system, then determine the rectangular coordinates of each point. So here, notice that r is equal to 2 and theta is equal to 30 degrees. So what does that mean? That means that point P is located 2 units from the origin in the positive direction, positive because, well, 2 is positive, on a ray making a 30-degree angle with the polar axis. Here's a picture that would show this point P. So this is point P right here. Let me label that for us. So this is point P right there. Okay, so this is the thing. This is 2 units away from the origin, right? And then this here is, this ray is making an angle of 30 degrees from the polar axis. Now, as far as finding rectangular coordinates for this point, we know that x is equal to r cosine of theta. So that means it's equal to 2 times cosine of 30 degrees. So it's 2 times root 3 over 2. That is to say, x is equal to root 3. Now y is equal to r sine of theta. So it's equal to 2 times sine of 30 degrees, which would then give us 2 times 1/2, which is equal to 1. So then point P here has the coordinates root 3, comma 1. These are the rectangular coordinates for that point P. The rectangular coordinates for the point 2, comma 30 degrees. Cool, let's look at another point, okay, another example. How about point Q, which has coordinates -4, comma 2 pi over 3. So in this case, let's be really clear here that r is -4 and theta is 2 pi over 3. Okay, let's show that. All right, so this is going to be here 2 pi over 3, right? 2 pi over 3. But we want to go -4 units. What that means is 4 units in the opposite direction. So therefore, point P would be 1, 2, 3, -4. So it would be right here. That's where point Q would be. So we went in the opposite direction, right? In the opposite direction from the pole on an extension of the 2 pi over 3 ray, okay? And this is our 2 pi over 3 right here. So we went in the opposite direction, 4 units. Now, let's find those x and y coordinates, all right? So x is equal to r times cosine theta. So it's equal to -4 times cosine of 2 pi over 3, which gives us -4 times, let's see, negative root 3 over 2, no, not root 3 over 2, excuse me, -1/2, which would be +2. Y will be equal to the product r sine theta, so it'll be -4 times sine of 2 pi over 3, so it'll be -4 times positive root 3 over 2, so it'll be -2 root 3. So the coordinates are 2, comma, -2 root 3. Check this out. Determine the following. 3 other pairs of polar coordinates for the point 5, comma, -110 degrees. So they want you to give 3 other options, okay? 3 other ways, basically 3 other ways to end up at this point. Now this point has 5 units away from the pole, 3, 4, and 5. And the angle is -110 degrees. Okay, so what we can do is we can get the supplement over here like this, that angle, but then go -5 units. So for example, let's see, we have -110 degrees, so this is an option. So -110 degrees plus 180 degrees, what would that give us? 70 degrees. So here would be 70 degrees, but instead of going 5 units, 1, 2, 3, 4, 5 units this way, landing here, remember we still want to end up here at this point. So how about 70 degrees, but then go -5 units. So 70 degrees and then -5 units could be an option. So here's a pair, right? A pair of polar coordinates instead of 5, -110. What else could we do? Well, what if we kept +5? So what if we still stayed at 5 units out from the pole, from the origin, but instead of -110 degrees, what if we got its coterminal one of least positive measure? So in other words, let me box this for us folks before I move away from it. What if I took -110 degrees and added 360 degrees to it? What would that give me? 250 degrees, wouldn't it? So that would still be this angle here. So it'd be coterminal, and then still 5 units out. So then another option then, therefore, would be 5 comma 250 degrees. That would be another option to get to this point. 250 degrees and then 5 units out. Okay? Now for a third pair, what I could do is, let's see, this is negative 110. If I keep going to the green ray, that would be negative 110 and then minus 180, correct? So let's do that. Let's figure out what that is real quick. So negative 110 degrees minus 180 degrees. In other words, keep going in that negative direction. That would give us negative 290 degrees. Degrees. There it is. Okay, so this is negative 110, negative 290. But let's make sure we go negative 5 units. So we want to go in the opposite direction there. So then here's a third pair. Negative 5 and then negative 290 degrees. Now, as you can probably imagine, there are, it's limitless. There are so many different ways you can write polar coordinates. There's basically an unlimited number of options. So in other words, while a given point in the plane can only have one pair of rectangular coordinates, this same point can have an infinite number of pairs of polar coordinates, okay? Check out this next part. Find one pair of coordinates, polar coordinates, for the point with rectangular coordinates 6, negative 6 root 3. In order to answer this question, we must remember that r squared is equal to x squared plus y squared, right? Which is the same thing as saying r is equal to the square root of x squared plus y squared. In this case, it would be 6 squared plus negative 6 root 3 squared. Of course, the square root of all of that. So in this case, r would be equal to the square root of 36 plus 36 times 3, correct? Let's keep going here. So then r would be equal to 36 plus 108. So r would be equal to 144, the square root of 144, so which is equal to 12. Okay, so we know what r is. Now remember that theta, as far as theta is concerned, let me come back up here. So r is 12. Let's not forget that, okay, everybody? Now theta must satisfy the following. Tangent of theta must be equal to y over x, as long as x is not 0. So in this case, your y value is negative 6 root 3, and your x value is 6. So then tangent of theta would be equal to negative root 3. Now, in order to figure out the right value of theta, remember that you are in quadrant number 4. How do I know that? Well, x is positive and y is negative. X is positive, y is negative. That puts me in quadrant number 4. Now, that's very important and also very easy to forget, all right? So be very careful. So in quadrant 1, my reference angle is going to be 60 degrees. But in quadrant number 4, that's going to be 300 degrees. So with my theta and my r value, I can say a pair polar coordinates can be 12, 300 degrees. Now, like we showed in the previous example, this set of polar coordinates here, there are infinitely many ways to write these, right? Coordinates. So this is just one possibility for the ordered pair 6, negative 6 root 3. Okay, check this out, guys. Example 3. For each rectangular equation, give the equivalent polar equation and then sketch its graph. First of all, let's let's acknowledge something. This equation in rectangular form is written in slope-intercept form. Okay, so this is y equals mx plus b form. So you and I already know that this is going to be a line whose slope is positive 2 and y-intercept is negative 4. Let's get the polar equation, the equivalent polar equation for this equation. So the first thing I'm going to do is get my, I'm going to write this in what we call standard form for a rectangular equation. In other words, I am going to get my x's and y's on the same side. Okay, so I basically subtracted y and added 4 to both sides. And then the next thing I'm going to do is I'm going to, remember this, guys, as I make my substitution here. Remember that x is equal to r cos theta, right? And then y is equal to r sine theta. I'm going to make that substitution right now in my equation. So then this will be 2 times r cos theta minus r sine theta equal to 4. All right, so no more x's and y's, but now r and theta is in the equation. So here, I don't need these parentheses. I could just say 2r cos theta minus r sine theta is equal to 4. What I would like to do next is factor out r. So if you factor out r, you'd have r times 2 cos theta minus sine theta is equal to 4. Which would then lead me to, if I divide both sides by 2 cos theta minus sine theta, I would have my final answer of r is equal to 4 divided by 2 cos theta minus sine theta. Look at this, everybody. This is the polar form, the polar equation for a line whose slope is positive 2 and y-intercept negative 4. Isn't that pretty amazing? So this is the polar equation for that linear equation. Let's graph the line now. To get this started, I show my polar coordinate system superimposed onto the rectangular coordinate system. I scale this out a little bit. And then let's not forget that the equation in rectangular form says that my slope is positive 2, my y-intercept is negative 4. So I know my line goes right through negative 4, right? And then the x-intercept, you can see that if you let y be 0 and solve for x, add 4 to the side and then divide by 2, your x-intercept would be 2. So that would be about right there, right? So here's a sketch of my line, okay? Going right through 2 on the, let me label that for us. That's 2. Going right through 2 on the positive x-axis and negative 4 on the negative y-axis. Cool, let's do another one of these. That was fun. Check out this one. X squared plus y squared is equal to 25. Now, if you will remember from maybe your algebra studies, this is the equation for a circle. A circle whose center is at the origin and whose radius is the square root of 25. That is to say the radius is 5 units, right? So the center is at the origin and the radius is 5 units. Now, as far as the polar equation, remember this. Let me write it on the side. Remember that r squared is equal to x squared plus y squared. So we can just make that substitution. This whole left-hand side is just r squared. Now, if I take the square root of both sides, I'll get that r is equal to 5 or r is equal to negative 5. Now, either one of these would be your answer. So r is equal to 5 or r equal to negative 5. So let's go ahead and box either one of these, okay? Either one of these. Basically, these graphs coincide with each other, okay? So the graph of r equal to 5 will be the same thing as the graph of r equal to negative 5. So both of these would be a circle centered at the origin with radius 5 units. So here's the graph of that circle. The center is at the origin and the radius is 5 units. Now check this out. Graph this polar equation. R is equal to 1 minus sine theta. Now this is going to be a really, really cool looking curve here. What we want to do is evaluate R for different values of theta. So basically plug in values of theta until you see a pattern appear and then just connect your points with a smooth curve. So what you could do here is create a table that is similar to this one, and you can start plugging in some values for theta. So for example, if I start with 0 degrees, sine of 0 degrees is 0, and r would be equal to 1 minus sine of theta. So in other words, r would be equal to 1 minus 0, which is 1. So therefore, one point that's on this curve is 1 comma 0 degrees. Cool? And you keep doing this. So let's do this again. Let's go, I don't know, maybe 30 degrees. That would be convenient, wouldn't it? Sine of 30 degrees would be 1/2. I'll write it as a decimal if you don't mind. R is 1 minus 1/2, which is 1/2. If I could squeeze that in there. So then this ordered pair here is 1/2, comma 30 degrees. And this is what you would want to do. I know it's a little time consuming, but you would want to do this for different values of theta until you get your curve. If I go for 45 degrees here, sine of 45 degrees is root 2 over 2. Okay, you can change that to a decimal if you'd like. Here, I'll do that. It might be just a little more convenient as far as plotting goes. So this is about 0.7. So r would be equal to 1 minus 0.7, which is about 0.3. Okay, so then this is 0.3, comma 45 degrees. Cool. Now these are just going to be sketches, right? So let's be very mindful of that. Sine of 60 degrees is root 3 over 2, which is 0.9. Okay, it's almost 1. So r is equal to 1 minus 0.9, which is equal to 0.1. Yikes. There, 0.1. So then this ordered pair is 0.1, comma 60 degrees. Let's go for 90 degrees. So sine of 90 degrees is 1. R is equal to 1 minus 1, which is 0. So then this ordered pair is 0, comma 90 degrees. Isn't this great, you guys? Now, I would suggest that you keep on going all the way through 360 degrees, which of course would be a duplicate of this first row here. Okay, I'm going to start plotting here. I invite you to continue to generate ordered pairs. So I'm going to start plotting some of these so I can show you. So one of them that I want to plot is, here I can show you, is 1, r is equal to 1, and then theta is 0 degrees. So that means you want to go 1 unit out from the pole, 1 unit out from the pole, and make sure the angle that is formed by that ray is 0 degrees. In other words, 1 unit out from the pole would be right here, and then the angle has to be 0 degrees. So this ray right here would be 0 degrees and 1 unit out. Okay, that's one point that's on the curve. Another point that's on the curve is 1/2, comma 30 degrees. So you are closer to the pole, but the angle is now 30 degrees. So if I can show that, I'll do the best I can here. So 1/2 and then 30 degrees, maybe about right here, everybody. Okay, this is about 1/2 units, 1/2 units away from the pole, and this angle here would be 30 degrees. Okay, and of course you can tell that I'm eyeballing this. Look at this. This is, let's do this one. 0.1, that's almost basically at the pole. That's almost 0, right? And 60 degrees. So something like right here, okay? That's really close. And then we have this point here, 0 units away from the pole, so you're right at the pole, and 90 degrees. So in other words, when you're at 90 degrees, you're actually on the pole right there. So far we have this curve, you guys. So far we have this curve. Now, if you keep going, you'll find that the rest of the curve behaves like this. So if you continue to generate ordered pairs and you connect the dots, really, then you find this graph, which looks like a heart shape, and we call it, therefore, a cardioid. So there's a lot of really cool looking graphs in this section. So I invite you to play around with them and give it a shot. Remember that you have a free graphing calculator, if I can do a little plug here, for Desmos. Desmos.com could also help you graph some of these polar curves so that you can get an idea of what they look like. And of course, the picture is going to come out way better than our hand-sketched curves. But anyway, if you're struggling with any of them, go to Desmos.com and punch them in, and it could give you an idea of what we're going for. This next one is really interesting. It's actually one of my favorites. R is equal to 4 times cosine 3 theta. So this one, I'll create a little table here so that we can start evaluating R for different values of theta. All right, so I have this table here, and I'm going to start plugging in values for theta. Now, I want to be smart about what I plug in, because whatever you plug in for theta will end up being tripled, right? 3 times theta. So if I start with 0 degrees, then 3 times theta, 3 times 0 degrees would still be 0 degrees, and cosine of 3 theta, cosine of 0 degrees, is 1. So therefore, R would be equal to 4 times 1, which is 4. So then the polar coordinates would be 4, 0 degrees. Now, if I try to be a little smart here about what I choose next, what if I go for 10 degrees? And the reason why I'm going for 10 degrees is because if I multiply 10 degrees by 3 theta would be 30 degrees, which is one of my special angles. Cosine of 30 degrees is root 3 over 2, which is 0.9. I'll just put 0.9. So R would be equal to 4 times 0.9. Which is equal to, let's see if I could, there, a little better. So this is about 3.6. So this is 3.6 comma 10 degrees. All right, so I kind of want to be smart about what I'm plugging in. Let's plug in, let's see, what would give us our next special angle? Well, let's go for 60 degrees. So I'm going to skip over 45 degrees just to kind of shorten this process a little bit. So I want 60 degrees here. So I know I'm going to end up tripling theta. So if I let theta be 20 degrees, triple 20 degrees, 3 times 20 degrees is 60 degrees. So that's what I'll plug in next. 3 times 20 degrees is 60 degrees, so that's 3 theta. Cosine of 60 degrees is 1/2. So R would be equal to 4 times 1/2, which is 2. So then it's 2 comma 20 degrees. Okay, let's jump to 30 degrees. 3 times 30 degrees is 90 degrees. Cosine of 90 degrees is 0. So then R would be equal to 4. Sorry, hold on. There we go. R is equal to 4 times 0, which of course is 0. So then the ordered pair is 0, comma 30 degrees. So what I would like you to do is to continue this process. I invite you to continue generating ordered pairs and then start connecting the dots. So watch how cool this graph turns out to be. Okay, so the first ordered pair that I want to plot, I want to show you, is 4 comma 0 degrees. Let's plot that one. 4 comma 0 degrees. So that means go out 4 units, 1, 2, 3, 4 units at 0 degrees. So there's that first point there, okay? That's 4 comma 0 degrees. The next one I want to show you is 3.6 So about 3.5, and at 10 degrees, okay? So at 10 degrees, basically, at 10 degrees, you're at about 3.5. So 10 degrees, about 3.5. So maybe about right there, okay, everybody? Give or take. Of course, we're doing this by hand, so be forgiving. At 20 degrees, you're out at 2 units, 2 units away from the pole. So at 2 units, 1, 2, you're about 20 degrees, okay? And then here, this point here, at 30 degrees, you're at 0 units away from the pole. In other words, at 30 degrees, you're right at the pole. So at 30 degrees, you're right at the pole. That would put you right at the pole. These are the only points that you and I have generated so far, and I invite you to continue to generate ordered pairs. And now I'm going to show you what the final curve would look like. So this is a rose curve, okay? It's called a rose. And what's really cool is that it has 3 what we call leaves. So 3 leaves, right? 3 leaves. And what's really cool is that the length of these leaves is 4 units. Look at, from the pole to here is 4, from the pole to here is 4, from the pole to here is 4 units. So I don't know if you noticed, but this number here gives us the length of the leaf, of each of the leaves, and this number here tells me how many leaves I have. So this is a rose curve. So it's called a rose, and here it is. That coefficient gives you the length of your leaves, right? It's actually the absolute value of that number gives you the length of the leaves, and then this tells you the number of leaves that you have. Now this is really interesting, so watch the following. If we were to graph this different equation here, it would also be a rose. So it actually follows the same kind of pattern of this equation, except, now watch this, your leaves would be length 3. So right here tells you the length of your leaf, right? But this is the part that's really interesting. You would not have 2 leaves here. You would actually have 2 times 2 number of leaves, 4 leaves altogether. So what I would like to do here is to draw a pattern for all of our rose curves. So all of our rose curves have equations of the following: a times sine of n theta and a times cosine of n theta. So here's a little summary for us. If n is odd, then that's how many leaves you have. You have n leaves. Like in our example that we did a little while ago, our n was 3, right? And we had 3 leaves. But if n is even, then you'll have 2 times n number of leaves. The absolute value of a always tells you the length of your leaves. So with that being said, and before we move on to something else, what if you had something like, let's just see if I can make something up here. So if you had r is equal to 5 times cosine of, I don't know, let's just say 4 theta, right? This would fall under the category of a rose curve, but how many leaves would you have? You would have, because n is even, you would have 2 times 4 number of leaves. So you would have 2 times 4, which is 8 leaves. And the length of your leaves will be the absolute value of 5, correct? So the absolute value of 5, this would be the length of the leaves. Okay? So you can use this pattern to confirm what your curves will look like even before you actually do all of the work. All right, this will be the last example, and notice what they're doing. It's the opposite direction of what we did earlier. They're giving us a polar equation. We have to go the other way around and convert it to a rectangular equation and then graph. Earlier in this lesson, we had a rectangular equation and converted it to a polar. So just notice that we're going the other direction. Now, to get this started, what I would invite you to do is to clear the fraction. So multiply both sides by 1 minus cosine theta. This is what we would have. Next, let's distribute the r value. So that would give you r minus r cos theta is equal to 1. Let me move this up a little bit. So what you would do next, maybe, is replace r with the square root of x squared plus y squared. That's what r is equal to. Minus, now do you remember what r cos theta is? That's equal to x. And equal to 1, like this. Cool. Now what I want to do is get rid of that square root, but before I do, let me isolate that square root. I'm going to move x to the other side. And now I will square both sides. When I square the left-hand side, it kind of eliminates the square root. And when I square the right-hand side, I'll get x, let me write it out. I'll get x plus 1 quantity squared, right? This is from me squaring both sides. And then we're almost there. I would have x squared plus y squared on the left, of course. And on the right, after I would FOIL that out, I would get x squared plus 2x plus 1. The x squared on the left and the x squared on the right would cancel. And then I'm left with just y squared is equal to 2x plus 1. So I can see right now, because I have only one variable being squared, I know for sure this is a parabola. Because it's the variable y that's being squared, I know this parabola opens either to the left or to the right. I'm going to continue going with this. I'm going to factor out a 2, and then this would be x plus 1/2. The reason why I did that is because this is a standard form for a parabola. Opening to the, well, now I can see that this coefficient is positive, so I know this parabola opens to the right. Cool. So make sure that you convert your equation and don't stop until you have something that is in standard form for a rectangular equation. So this is our rectangular equation. Let me remind you of where we started. So we started with r is equal to, we had 1 over 1 minus cosine theta. So we have the rectangular equation on top, and we have the polar equation down below. What we want to do is graph this parabola. Because you and I put the rectangular equation in standard form, we know that the vertex of our parabola is going to be negative 1/2, comma 0, negative 1/2, comma 0. Okay, I scaled out my axes. I think this will be good. You know what I will do for us is, I want you to notice that I'm going to look at this rectangular form, everybody, okay? You will have, let's find our Y-intercepts, okay? It'll touch your y-axis twice. So the way we do that, remember, is to plug in 0 for x. So you can see that you're going to get y squared is equal to 1. When you take the square root of both sides, you get plus or minus the square root of 1, which is just 1. So you can see your parabola will go through y equal to positive 1 and y equal to negative 1. And we know that the x-intercept is basically the vertex of the graph, which is negative 1/2. You can confirm that by letting y be 0 and solving for x. So you can see that our parabola will open to the right, and it will look something like this. Okay, so there's the graph. This was a really cool example. I hope you enjoyed it. We started with the polar curve. R is equal to 1 over 1 minus cosine theta. Converted it to this rectangular form. Notice that it's a parabola opening to the right, and we graphed it. This completes this section, 8.5 polar equations and graphs. I hope you have fun.